Welcome to Orbital Debris Oversight, fostering space domain awareness through ITU compliance. I'm Nicholas Barr, and the SEAS internship has helped guide my decision to pursue a career in astronautical engineering in the United States Space Force.
I'm Taaha, and the SEAS opportunity has been a great experience for me to continue honing my skills in computer science.
I'm Esai, and SEAS has opened up my mind to the possibilities of my career.
I'm Noelle Kim, and C solidified my interest in engineering by giving me real-world experiences in the field.
I'm Diana, and SEAS has helped me learn more about our satellites and helped me pursue my passion for engineering.
I'm Riley, and SEAS has given me a more direct experience with researching astrophysics.
It is estimated that there are around 100 trillion pieces of debris in Earth orbit. This can pose a threat to launches and existing satellites due to high velocities. However, what we are concerned about in this project is geostationary orbit, or GEO. GEO sits exactly 35,786 kilometers above the ground. It is mainly used for telecommunications and GPS. While there is little orbital debris in GEO, the number is quickly expanding and needs to be kept clear so geosatellites stay safe. Geostationary orbits offer numerous benefits to humanity because of their unique positioning. Their stationary nature allows them to provide continuous support to ground-based objects, making them indispensable for various applications. However, their crucial role also means that maintaining their functionality is vital. Even a small amount of orbital debris can damage or destroy these satellites, potentially disrupting the essential services they provide. The solution to this is physical slots in the ITU. Physical slots are defined by a longitude to the equator, typically separated by some degrees to avoid interference. This is established by the ITU, which is a branch of the UN that specializes in communication technologies. ITU compliance ensures the safety of satellites as long as it is followed correctly.
So with this background, the question that we decided we wanted to focus on was, what is the distribution of geosatellite compliance by country? And the reason we wanted to focus on this is because we decided that if we were to implement a solution in the future to encourage compliance internationally, we would need to know which countries are the most responsible for the population of non-compliant satellites, and that would help us, determine how a solution should be administered across different countries. So that led into our project goals, which was first to analyze the current geoposition compliance situation, and second, to come up with some solutions or starting points for improvement in these regulations. And our inspiration for this work was a 2024 thesis by PhD Thomas Roberts at MIT. The novelty of his work was that he created a method for determining if satellites were compliant based on only publicly available data, which had never been done before. And so we took inspiration from this by studying his program, deciding we were going to write our own Python program that was tailored to the needs of our project based on similar definitions of compliance. And the reason we did this is because we wanted to expand our experience in Python and also create something that would specifically show us distributions of countries that we could easily reproduce and share.
Yep, so ITU compliance basically assigns a specific compliance zone to different satellites as network allocations. So if a satellite is within that zone, then they are compliant. If they're outside of an assigned zone, then they are non-compliant. So specific satellite longitudinal information is easily accessible and available to the public, as well as the ITU network assignments, which are publicly disclosed. The problem is the specific satellite network pairs are not openly available. So you don't know which satellite is supposed to be in which zone. So here we created a program that sort of matches different satellites and the specific zones that they could be a part of in order to determine whether they might be compliant or not. So here our program provides an end-to-end solution for determining satellite compliance. So we have an input user interface where you can determine like specifically by satellite, by country and whatnot. Then we have a data curation method, which sort of brings in information from different public sources. And then we insert this into a matching algorithm, which matches different satellite positions to their possible network compliant allocations. And then it results in statistical analysis, which we can do to see which country is the most compliant, least compliant, and other forms of information. So here's the methodology for overall matching algorithm pipeline. We take different signals, such as the daily satellite longitude, the brought to use launch date, and other pieces of information. We bring it into a matching system along with the registered ITU network band allocations, and we determine if the satellites are within 1 degree, 0.5 degree, 0.1 degree, or whatnot, based on the different signals that we input. So this creates a short list of possible network matches, which can be assigned to the specific satellite. So if there are no networks matched to the satellite, then the satellite has to be non-compliant because it's not legally allowed to be in that zone. And if there's more than one or more network matches, then the satellite is possibly compliant because it is allowed legally to be in that zone.
The graphs on this slide demonstrate the quantity of satellites deployed by each country, as well as the number of non-compliant satellites per country. As can be seen, the United States and People's Republic of China are the primary deployers of satellites by a significant margin, as they are two of the first countries to become involved with spacecraft. The data indicates that countries with longer space programs are more likely to be non-compliant, as they are more comfortable and familiar with the systems. There was also a difference between the non-compliant numbers from countries and from international organizations. The EUTE and SES were noticeably more compliant than the Commonwealth of Independent States and Canada, both of which had less deployed satellites. The countries with more established space programs may also have higher non-compliance due to increased power within the space system. This would explain why many important members of space programs, such as the US, People's Republic of China, and Canada, have larger numbers and percentages of non-compliance. In this graph, Angola and Bermuda are the most non-compliant countries, followed far behind by Canada. However, both Angola and Bermuda have only 1 to 2 satellites deployed, meaning that these numbers are actually deceptive. The right graph shows more useful data, as the United States and People's Republic of China combined consist of over 50% of all non-compliant satellites, with most small outliers like Angola or Bermuda consisting of a very small number of satellites, all of which were non-compliant.
In the graph to the left, it can be seen that both compliant and non-compliant satellite launches are gradually increasing at a steady rate. After a noticeable increase in 2000, the number of compliant satellite launches is very high, with non-compliant launches being relatively rare. This is important to consider as it seems that despite some countries having very high non-compliance rates, most satellites remain compliant, a trend which seems to be improving. This graph displays satellite locations across the longitudinal spectrum, with some regions holding dominance where larger and more established countries are. The United States, for example, is represented in light blue and is dominating over the Western Hemisphere. In the Eastern Hemisphere, China and Russia dominate in the colors light, dark gray, and lime. Overall, it seems that countries with stronger space programs have less compliance, with some outliers where a few non-compliant spacecraft are the majority of a small number of satellites.
Altogether, we found that larger space programs like the US and China had the highest numbers of non-compliant satellites, whereas newer space programs like Angola and Bermuda had the highest percentages of non-compliance. This issue ultimately threatens key networks of weather monitoring, communications, the internet, and more. Our research can guide future action to ensure compliance for large and small space programs alike so that we can keep these critical GEO satellites safe. And since non-compliance both sources from and affects various countries, our findings highlight the need for international cooperation on such solutions. Moving forward, various space agencies must collaborate on international guidelines and agree to enforce IT regulations at the national level, such as through fines and licensing regulations. Additionally, we must simplify current global frameworks, as the ITU identifies overly complex regulations as a major barrier to compliance. We can also implement a novel reward/penalty system to incentivize improvement by limiting the abilities of non-compliant nations to launch new satellite missions or access shared resources like the Deep Space Network. And finally, future policymakers can aid newer developing space programs in improving their compliance rates, such as through assistance in drafting national regulations and through capacity building efforts like the satellite regulatory workshops. In the future, we can expand the scope of our compliance analysis to electromagnetic spectrum bands to check for stray signals. We can also survey space agencies and individual satellite operators about the challenges they face in following IT regulations. Furthermore, we can analyze how causal factors like national policies or access to technology can affect different countries' compliance rates. And finally, we can quantify the relationship between non-compliance and the risk for debris accumulation, space traffic, collisions, and signal interference.
These are our references. And we'd like to give a special thanks to our project mentor, Ms. Karra, as well as Ms. Baggio and Ms. Miller, the coordinators of the SEAS program. Thank you for all your guidance and for organizing this program. And thank you also for everyone else watching at home. We had a great time doing this project and we're glad we were able to share it with you.